parallel plate capacitor with dielectric and conducting slab inside. Alright, as we already discussed in our offline class about the parallel plate capacitor, so you also know about the capacitance of parallel plate capacitor and the energy stored in the capacitor. Alright, so today we are going to discuss that what will happen when we placed a dielectric or conducting slab between the plates of the capacitor. So what if its capacitance increase or decrease, that we will see in the video. Alright, so just start the topic, that is the capacitor and what capacitor, that is parallel plate capacitor, parallel plate capacitor. Alright, with a dielectric and conducting slab inside. So you guys also know of the slab. What is the slab? Then slab is a rectangular sheet with a thickness T. Basically, you can say that is slab. All right. So let's just start with the conducting slab, because when we go for a dielectric slab, there is a particular topic, the dielectric polarization, that we need to know before to discuss this topic. So first we discuss the conducting slab, then we go for the dielectric slab. All right, so here for conducting slab, so here we have a parallel plate capacitor, and just draw it in 2D. All right, now this is the positive sheet, positive plate, you can see, and this is the negative plate. Now here we consider that the area of the sheet, that is A, and the distance between the plate is D. Now we already discussed the capacitance when no plates, no sheets is placed between the capacitor. Then the capacitance of the capacitor is C is equal to, we just denoted C naught. C naught describe that there is nothing between the plates of the capacitor. All right, and the C naught is equal to epsilon naught A over D, where the epsilon naught is the permittivity of the free space and A is the area of the plate and D is the distance between the plate. Basically, we already mentioned it over here. All right, so what happened when we placed a conducting slab over between the plates of the capacitor? So here I introduce a slab, that is conducting slab, made of metal, any kind of metal that is conductor. We all know about that. So first we have to know that what happened when a conductor is placed in an electric field. So all we know that between the plate of the capacitor there is existence of an electric field. So what happened when we placed a conductor in an external electric field? So according to the Gauss, we all know when you placed a conductor in an external electric field, the net electric field inside a conductor is always zero, no matter your conductor is hollow or solid. All right, so here if the distance is D and the electric field is before we place the slab, electric field cover all over the space between the plates. But when we introduce the slab between the plate, the net electric field in the region the slab covers is 0. The electric field inside the slab, that is 0. It means if the thickness of the slab is T, so to the T thickness the electric field region is 0. Now the electric field only covers this remaining region, alright. The electric field now exists in only the remaining region. What is the remaining region? That is D minus T, alright. So when we placed a conducting slab inside the electric field, slab between the plates of capacitor then the net electric field inside the conductor is 0. So the capacitance now become, that is C is equal to epsilon naught A. What is A? A is the area of the plates upon D minus T. Epsilon naught upon D minus T, because this is the only remaining region where the electric field is now in existence. So if we compare these two capacitance when there is no place inside and when there is a place there is a slab inside the plates, alright. In the first case there is no slab inside the plates, and in the second case there is a slab, that conducting slab, placed inside them. Now if we compare these two capacitance, so from this equation we can write that C is equal to epsilon naught A over, now D is taken as a common in this term in denominator, that is 1 minus T over D. Now if we compare these two, epsilon naught A over D over here to this term, so we find that epsilon naught A over D is equal to C naught, that is the capacitance of capacitor when there is nothing inside, alright. That is the, now we just replace this term epsilon naught A over D with C naught, that will become C is equal to C naught over 1 minus T over D, alright. So this is the basic relation between the capacitance of the capacitor. So here we can see that the capacitance of the capacitor is just increased when we introduce a conducting slab, alright, because the denominator is just keep decreasing. So in that case the total value of capacitance increased, alright. Now we moving further for the dielectric slab. Now we are just talking about the dielectric slab, but before that we just need to know what is the dielectric polarization. So to discuss the dielectric polarization, so as we already discussed in the dipole, there are two kind of dipole. First is polar and non-polar dipole. What are the difference between the polar and non-polar dipole? As the polar dipole has its own dipolic moment when there is a field or not any field present in a space, alright. So first we consider that is a plate with a polar moment dipolic. Now it means there is positive and negative centers are apart from each other. So this the dipolic moment property, the dipolic property without any external electric field, but they are randomly oriented. When there is no electric field, they are randomly oriented. So I'll just write the direction. As we know, the direction of the dipole is from negative to positive side, so it is represented in this term by an arrow. So when there is no external electric field, this is the polar dipole. These are the polar dipole, when there is no external electric field, in that particular case the polar dipole are randomly oriented in a field, just like this, any random direction they are oriented. And when we talk about the non-polar dipole without any external electric field are not showing any dipolic property, because their positive and negative centers are coincide at one point, just like this, that are positive and the same point this is negative, so they are coincide, so they do not show any dipolic property without any external field. So what happened when we placed these two slabs in an external electric field region, that is positive negative, that is positive negative, positive negative, and so on basically. All right, these are the non-polar dipoles, non-polar dipole. All right, so what is the basic difference? These non-polar dipoles doesn't show any dipolic property when there is no electric field present. All right, while the polar dipole shows the dipolic property, but they are randomly oriented. They don't have any particular direction, the uniform direction. They are randomly oriented in any direction. So there is no net dipole moment for a body, for a complete body basically. So what happened when we place these two in an external electric field? All right, now these two sheets, I'll just do it here. Now we create an external electric field. So for that, here two sides, that is, first one is created as positive side and second one is negative side. So an external electric field is just introduced here, that is E, or you can say E naught. So what happened then? As we know, the dipole just move itself in the direction of the electric field, and you can say the dipole is aligned in the direction of external electric field. So now these all dipoles will just moving in this way. So now they have a uniform direction. All right, and what about the non-polar? So they behave as same. Now the non-polar dipole is also behave as a dipole now, and they also align itself into the direction of external electric field. So when we introduce an external electric field in a dipole, and when external electric field around the dipoles, so no matter they are the polar or non-polar, they both align themselves in the direction of electric field. They both behave the same as in the condition of external electric field is present in that space, if any. So here we can see that the dipole align itself in the direction of external electric field, no matter when they are polar and non-polar. So there is a net external electric field, then net inside electric field generated inside the dielectric material. What is this? This is the dielectric material. Dielectric material. Both slabs, these both slabs are made of dielectric material basically. We already discussed the conducting slab. This is the conducting material, that is dielectric material. Yeah, you get it right, the dielectric material which do not conduct any electricity. So the dielectric material have two conditions, the polar dipole and non-polar dipole. Then when there is no external electric field present, they both behave as separate things. The polar dipole shows the dipolic property, but not net dipole present in that body, while the non-polar dipole material does not show any dipolic moment. But when an external electric field is created over that space, they both represent the same property. Now they both align themselves in the direction of external electric field. All right. So what happened? These material, these slabs create an inside net electric field. Actually, if we're talking about the real thing, the net positive and negative centers of these materials is created as the positive side attract its negative points and the negative side attract its positive charges. So there is net internal electric field created, that is represented by EP. EP means electric field by polarization. That particular thing is called dielectric polarization. Yes, you get it right. The things in which the dipole arrange itself in the direction of electric field, it happens in certain materials, then this condition is known as dielectric polarization. So here we see that when you placed a slab between inside an external electric field, there is a net electric field generated inside the plate, while in the case of conducting plate, there is the net electric field inside the conducting plate is 0. All right. So the net EP, that is the electric field generated by the polarization, dielectric polarization, that is EP, that is opposite, that is created opposite to the external electric field. So the net electric field inside, that is E net, if we are talking about, that will become E outside minus EP, that is working in the direction of the field, basically the net electric field inside the plate. All right. So now I hope you guys understand this. Now we are just moving to our final topic, that is the parallel plate capacitor when a dielectric slab placed inside. All right. So our second topic is capacitor with a dielectric slab inside. All right. Yeah, there's no one is watching, that's why I'm using this language. If someone is there, I can understand, guys. All right, no problem. Capacitor with a dielectric slab inside. All right. Now here is a capacitor, parallel plate capacitor. All right. This is the positive side and the negative side. All right. So when there is no slab placed inside, the capacitance, same, that is C naught is equal to epsilon naught A upon D, and you get it right that A is the area of the sheets and plates basically, and the D is the distance between them. Now we introduce a slab made of a dielectric material which do not conduct any electricity basically. So there is an electric field generated outside the net external electric field, that is the external E naught, and the field generated inside the plate is known as EP, electric field generated by the polarization, that is called EP. So the net electric field E is equal to the E naught minus EP. All right, and direction is the same as outside. So the net electric field inside the plate is equal to E naught minus EP. E naught means E outer, you can say in the both ways. All right. So when we placed a slab inside, or which slab, the dielectric slab inside the plates of capacitor, inside the dielectric slab of the capacitor, then what happened? An polarizing electric field is generated inside the slab, which has its direction opposite to the external electric field. All right. So the net electric field inside that is E is equal to E naught minus EP. Now here, as we know that we already discussed in our first chapter, the dielectric constant K is also referred as the relative permittivity, that is ER, is equal to F naught over Fm. Fm basically refer to the medium. You can see the F naught over F. So it also write as E naught over E. This is the relation between the electric field in when there is no medium inside and when the dielectric medium is placed. So E is dielectric medium when the dielectric medium, and E naught when there is no medium. Alright, so the relation that K is equal to E naught over E. Alright, and this we can write as the ER also. So ER and K both are the same things basically. This is called dielectric constant and relative permittivity, both have the same values, alright, for a particular reason. So here then we can find the value of E. E is equal to E naught over K. Basically this is the relation between the E and E naught, alright. So the net potential that is developed between the plate is V is equal to, we know that V is equal to ED. So what is the E? So there's two E's. The first, that E naught, that is in the region of D minus T, and what is T? T is the thickness of the slab as well. Alright, so E naught D minus T, that is the outer electric field, plus E into T. Basically what is E? E is this electric field which is developed inside the dielectric slab. Alright, now just replace this E with this term so that we can take the E naught outside. So V is equal to E naught D minus T plus E naught over K into T. Now take the E naught out, take as a common, then D minus T plus T over K. Alright, now put the value of V in this formula. So the net formula, that is C is equal to Q over V. Alright, and Q is equal to epsilon naught, sigma A. Sigma is the surface charge density. Alright, so C is equal to Q, that is sigma A over, what is V? V is E naught D minus T plus T upon K. What is the value of E naught? E naught, the electric field between the plates, that is sigma upon epsilon naught. Alright, now replace this value E naught with sigma over epsilon naught, that C is equal to sigma A over sigma over epsilon naught, that is D minus T plus T over K. Alright, now this sigma will cancel the sigma in the numerator. The C is equal to epsilon naught A over D minus T plus T upon K. So this is the net capacitance when the dielectric slab is placed between the plate of the capacitor. Alright, so here we can see in this case the net capacitance is increasing also. Alright, so in the both cases, when you place whether you place dielectric slab or conducting slab, the net capacitance of the capacitor will increase up. Alright, so this is all for today, guys. Thank you. I'm your teacher Ashutosh Sharma. Thank you guys. All right.